In the previous two episodes, we have been discussing the intelligence density per gigabyte of model memory, a metric proposed by Elon Musk in a recent podcast interview. Last week, we pointed out the problem with having important constructs like intelligence defined in terms of an agent's performance on a measure like FrontierMath or AGI Arc2. The analogy we used was defining the concept of the weight of an object in terms of the stretch of the spring the object is attached to. The stretch of a spring, in the absence of a more principled, theoretically grounded definition of inertial mass, may be adequate if we want to compare the weight of two objects as measured by the same spring, but it is completely useless for the rest of physics as a discipline studying objects from subatomic particles to stars and galaxies. Today, I will propose a principled approach to measuring intelligence, which will help us to define the intelligence density as a non-circular, theoretically grounded construct. I'm Alex Chadyuk, and this is AGI. Listen every Monday morning on your favorite podcast platform. An all-encompassing definition of intelligence I proposed a while back goes as the twofold capability to learn the rules of the new environment an agent operates in, and then to exploit those rules to achieve the agent's goals while adhering to certain voluntary behavioral constraints. This definition packs a lot of meaning, which is unsurprising for a concept as complex as that of intelligence. Today, we will focus on the first part, the capability to learn the rules of a new environment. This capability has enough complexity in itself. It calls for an ability to generalize from prior knowledge, formulate testable hypotheses based on this generalization, and integrating the observed outcomes of empirical tests into the knowledge base. But all this boils down to plausible reasoning about uncertain propositions, something that we talked about at length in earlier episodes. An intelligent agent is presented with a novel situation and a task or a goal that has a certain level of uncertainty. If the uncertainty is represented by some mathematical probability function, we can actually measure the level of uncertainty that the agent is dealing with. This measure of uncertainty is called entropy, which is the foundational concept of the theory of information developed by Claude Shannon in the middle of the 20th century.
When the AI agent applies its knowledge and its reasoning capability to reduce the uncertainty of the problem at hand, this results in the reduction of entropy. A change in entropy stands for a principled, theoretically justified definition of information. So now we can use this independent theory-grounded definition of information to measure the intelligence of the agent that was able to apply its knowledge and reasoning to the reduction of uncertainty of a given problem. Notice that there still has to be a problem and its surrounding context that frames the uncertainty we ask the agent to reduce. For this, we can use any modern AI evaluation problem set like AGI Arc2 or FrontierMath we mentioned before, or any other unsaturated eval, in other words, the one that AI does not simply knock out of the park. But what we are interested in is not the percentage of the problem set solved by the agent, but the reduction of uncertainty, which equals to the amount of information produced by the agent's correct solutions to the problems in the problem set. In Shannon's information theory, as you might have guessed, the amount of information is measured in bytes. So now we can assess the capability of an intelligent agent to generalize its prior knowledge to novel task by the reduction of uncertainty, measured in bytes, that the agent is capable to achieve through reasoning about these tasks. The ability to generalize from prior knowledge is only one part of our much more complex definition of intelligence, but it is often called out as the key differentiating factor of the artificial general intelligence, or AGI. Notice that our being able to measure the agent's capability to generalize in bytes rather than in the test percentage score is similar to a transition from measuring object's weight in inches of spring stretch to measuring the object's mass in pounds. It allows us to use different springs to measure different objects of the same mass, observe a different amount of stretch, and still come back to the same amount in pounds. Similarly, we can assess different AI models with different evaluation tests, but being able to translate the test percentage scores into generalization output in bytes allows us to make direct, independent, and scientifically principled comparison of the generalization capability of different AI models. To make this comparison more fair, we can divide the model's generalization output in bytes by the size of the model's neural network in gigabytes to get a generalization ratio. As I said, generalization is only one part of the artificial general intelligence definition, but the logic that we used to arrive at our generalization ratio gives you an idea of the kind of the principled scientific approach I call for in measuring the intelligence density proposed by Elon Musk. Thank you for listening and subscribing. Until next Monday, my friends. I'm Alex Chadyuk, and this is AGI.